Good morning, AP Physics students. I'm recording from a different room today, so that way the baby boy can be downstairs making all the noise he wants, and the wife can play Animal Crossing on the TV. So we'll try this out, see how it works, and let's just head on into it. Also, on the YouTube channel, I'm going to try to make like an engineering channel and a physics channel because people are subscribing, so that way you only get the lessons you need. Obviously, just check E2SD for everything. Office hours went great. Some kids stopped by. It all works. It's optional, but basically I'm online. You can talk to me if no one's there. I'm probably just going to be typing grades into the gradebook. Gradebook is going to go live. You'll see grades popping in as we are definitely doing distance learning until at least beginning of May. Let's head into momentum. All right, so now we're looking at momentum graphs. And so here we have, it's a truck of mass m moving with a velocity of v. Let me get a highlighter selected here. It works. Yes, it does. All right, so looking over here, you have a truck with a mass m and a velocity of v, and there's two cases. In both cases, it has the same speed and the same mass, just it has to do like a really quick stop or versus a very long stop. And when you look at these graphs, it's important to look at what the y and the x-axis is in order to understand what you should be graphing and in what way. And the idea behind the question is that here's where your starting momentum is. And I want to remind you that momentum is calculated with mass times velocity. So think about what the starting momentum of the truck would be, and then think about the impulse that would happen during a gentle stop and an emergency stop. And then the final momentum for both of these is gonna be zero. That's the idea, is that it should be coming to a rest in these. But these should be graphs. It's kind of an interesting question. And just give it a try, and then we'll go over the answers. And then over here, you have different vehicles because they have different masses. Look carefully. 3,000, 100, 1,000, and 2,000. They have actually different amounts of mass, and they have some of them have different velocities. Some have the same velocities. See if you can answer the question about which barrier would be the take the longest time versus the shortest time, and explain how you come up with your answer. All of this is basically review, but we're heading into graphs. Go ahead and pause it, give you a chance, and you have to pause it actually. Okay, let's go ahead and move forward. All right, so I'm not in love with their graphs because it's a little confusing, like what a velocity versus mass is. But I do really like the question, and I really like the middle of the question. It's solid. So the idea is that both of these are exactly the same. Like that's all they wanted you to see, that they should be exactly the same. And then this area is negative, and the reason it's negative is because it's a negative force and it's slowing the object down. And the idea is this is actually a plus sign. I forgot to kind of point that out. And that the idea is no matter how much, well, both these vehicles have the same exact starting momentum, and they're both going to come to a stop. But the question is it going to be a large amount of force for a short time, like it is down here, or is it going to be a small amount of force for a long time, like it is over there? And because either way you end up with the same area. That's kind of the big idea here, is that this area and that area, they're equal, and these areas are actually equal too, because these two are equal. All right, let's take a look at the other question, which is very closely related. So the basic idea is that these barriers all provide equal force. So whatever object has the most momentum is going to take the longest time to stop. Looks like, oh, there's A, B, C, and D. So this object, so really all you have to do is multiply their masses times their velocities, and you get the idea. So this one is 30,000. This one is 2,000. This one is 3. Looks like 30,000 again. And this one is, looks like 40,000. Yeah. So D is the biggest, A and C match, and B is the last. And it's really just ranking their momentums. Whoever has the most momentum is going to take the most time to stop. All right, so let's actually head into what's the new thing we're learning today. So the new thing we're learning today is force versus time graphs. Force multiplied by time is actually impulse, as it's kind of, let me get my highlighter. Impulse. And so impulse equals change in momentum. And so the idea is that if you have something that's a hard collision versus a soft collision, you have the same area, the same impulse, the same change in momentum is occurring. It's just a question of whether that change is very, very flat or if it's spread out. This is weirdly related to the whole flattening the curve thing that's going on, why we're staying indoors, is because we kind of think that the same number of people are going to get infected no matter what we do. We just need to make sure those people don't get affected at the same time so that our hospitals get overwhelmed. So that's why we're all staying indoors, because we still know that people are going to get sick. It's just a question of how many people can be sick at once, and we don't want this basically. Then we run out of ventilators, and so we're trying to do this. And same thing when you're in your car and you get in a crash. The reason we want crumple zones is because we don't want this. Either way, your car is going to have the same area. It's going to experience the same slowdown. The question is, can we make that collision take a really long time to lower the force on you? And also, now we can understand that this is a way of representing momentum changes, or the force multiplied by time. So let's take a look at an example problem that gives us information in a graph. Okay, so we have a graph here that has force over time for a car of 5 kilograms. And the question says that the car is going to actually start from rest. That's important to know that this graph doesn't tell you how fast the car is moving. So I had to tell you that it's from rest. So now the question is, how fast is it? Oh, so what's the change in momentum? Well, impulse equals change in momentum. So the area of this graph is equal to the actual change in momentum that occurs, which is what's going on over here. So area is change in momentum. That's kind of our big idea right now. And so you just have to calculate the area of the square and the triangles. No calculus in this class. That's a big useful thing in college level physics, is being able to integrate this. So the area of this graph is 140. So the change of momentum is 140 kilogram meters per second. Remember that momentum is just mass multiplied by velocity. That's all momentum is. So it has units of mass multiplied by units of velocity. And so question 2 says, how fast is it moving after 10 seconds? You have to know the initial velocity, because the graph only tells you the change in momentum. It doesn't actually tell you how much momentum it has. So, but I can use the change in momentum formula, and I can plug in my initial velocity from rest and solve for my final velocity, which apparently 28 meters per second. Now we can go to number 3. Number 3 says, if the object is brought to a stop in 3 seconds, what's the impulse required? This is a trick question. Doesn't matter what the time is. What's the impulse required? Well, what's the area of that graph? Because that's how much impulse is needed, because the impulse equals the change in momentum. So how much impulse is needed? It's how much momentum do you have? 140 is the answer. Here's all my little written explanation down here. That the impulse is the change in momentum. So if you got 140 kilogram meters per second of momentum to deal with, that's how much impulse it's going to take you to get rid of it. Don't worry about the positive or negative sign for that one. It's really just asking what's the magnitude or how much. Number 4, a constant force is applied for those 3 seconds. What is the value of this force? Okay, apparently I don't want to redo this whole thing. Clearly I forgot to add a little bit of text there. Constant force applied was the value of force in order to stop the object, required to stop. Okay. So the question, and I'll edit this for the uploaded notes. So what is the force required to stop the object? So to stop it, I just want to get rid of all this momentum. So I set that over here to be the momentum that I have, 140. And if I use 3 seconds of time, my force is 46. And you can imagine if we made time go up, force would go down, and vice versa. Now, what about negatives in momentums and impulses? Well, we actually saw some negatives in the bell work. And here's an example that has a graph that goes both directions. It's not too terribly exciting. But this represents a positive change in momentum, and this represents a negative change in momentum because it's just the direction of force. You know, force can act forward, and force can also act backwards, and so there can be acceleration in the positive direction or acceleration in the negative direction. So momentum has a positive and negative sign because remember that momentum is mass times velocity, and velocity has a direction. Therefore, momentum's going to probably need to have the same direction, and it does. Um, Same thing with like F equals ma. Acceleration has a direction, and so does force. Um, for this particular problem, how do we solve it? Well, I got the solution on the next slide. We'll just move forward. So for this one, you just have to, we can call these impulses, or we can call them changes in momentum because it's the same thing. So we need to know the initial velocity, or the question can't be answered, and then all we gotta do is find the areas. So the area, the first graph is looks like 10 by 3. 10 by 5. Okay, so it's 25. So this area is 25. This area here is looks like 10, maybe negative 10. So that's an overall the change in momentum that happened here is a positive 15 kilogram meters per second. So if we know that's our change in momentum, we can set that equal to mass change in velocity, velocity initial. I believe that's right down here, actually. Yeah, highlighter. So they're setting 15 equal to 5, velocity final minus initial, and we can get that our initial velocity needed to be 6. Or sorry, our final velocity would be 6 if our initial velocity was 3. Be very careful with your finals and your initials. Change is always final minus initial. All right, take a look at the homework. There's no skill check today because we're doing those skill checks every other day if you haven't figured that out yet. And then we are going to try an online quiz. I'm not exactly sure how it's going to work yet. I have a few ideas. I'll give you an update when I've figured it out. Maybe we won't do it, and then we'll just do it when we come back. But part of me really wants to try to do an online quiz. And so we might give that a go, but just keep up with these lessons for now, and I'll let you know when I have more information, probably next Monday. Stay safe out there, guys. Drop by office hours if you're confused. The next office hours is Thursday from 10 to noon. Have a good day.